Sorry, my last video got cut off. Continuing on with this third example for electric potential energy of a dipole, we are given our starting point to be at a specific angle to our electric field as it rotates in this direction. So this is our initial, and it rotates to our final direction. We want to find what the electric potential energy is for this example. So to start things off, we are going to be using our work equation. But in this case, what is changing is our angle. So we're going to use our angles to define our bounds, and F ds, or d theta, sorry. So in this case, we want to take a look at, from our previous one, our torsion of our dipole moment times our electric field, sine theta. Right, in this case, since we're rotating clockwise, rotation equals negative k hat direction. So we're going to use this as our force in our work equation. So let me just underline this so it'll be a little easier to follow. So this is work, final, and our initial. And then we're going to plug this in. So this is negative because of our rotations. This is negative dipole moment times electric field. Okay, and when we integrate that, we can kick these two out. So this is negative dipole moment times electric field. And we integrate our sine that's left in here. This will give us negative dipole moment times electric field. And this is cos of our final minus cos of our initial. So then for our electric potential energy, this is like saying, so if we distributed our cos in there, this looks an awful lot like our dot product. So we can express this as plus at our initial. And if we move it around a bit, we can do, so it's P dot E. This is initial minus our final. So that is our third example for electric potential energy. And now we're going to talk about electric potential. So electric potential is defined by symbol V, and this is over our electric potential energy over Q. So if we wanted the total change of, say, from point B to point A, if we went from A to B, this is our final and our initial points. This would be like saying our change of our electric potential, B minus A, over Q. So we can also think of our change in our potential energy, in our potential energy as from our positive minus our negative quantities. So if we look at this example here, each plate has 5 volts. So where this is positive 5 volts, and our bottom is negative. So if we were to look at our first one, for A, at this point of measurement, this gives a difference of positive 2.5, because we're measuring halfway, and negative 2.5. So if we wanted to find, so we take from our positive minus our negative, so then that's 2.5 volts in our red minus our negative 2.5 volts in blue. And this is going to equal 5 volts. And if we did it at B, where our point of measurement is at V equals 0, at the bottom of our plate, then this would be just each value as it owns. That's 5 minus, and then our distance of our point of measurement from here is 0, so that's minus 0. Let me just define this, where this is 5, and this is also equal to 5 volts. So no matter where you're measuring it, it's always going to stay consistent in between parallel plates. Now let's take a look at this example here. So in this problem, let's start out by labeling what we know. So we are measuring at a point of 0x and 4 upwards. So that means we are going to be taking into consideration both of these charges and what electric potential they cause due to their charge at this certain point. So for Q1, we're going to need this separation distance of R1, where our Q1 is 3 microcoulombs, and our charge of Q2 is negative 5 microcoulombs at separation distance R2. So starting with our first one, we are at negative 2, so I'm just going to put 2, and at a height of 4. So when we find our R1, that's equal to 2 squared plus 4 squared, which is equal to 4 plus 16, which is equal to 20 cubed, square root of 20. And that is roughly 4.472 meters. So to find V1, we take 1 over 4 pi epsilon 0, our charge, over our separation distance. So then this is equal to 8.99 times 10 to the 9, and this is 3 times 10 to the negative 6 coulombs over 4.472 meters, and this becomes 8.99 times 10 to the 9 times 3 times 10 to the negative 6 divided by 4.472, and this gives us 6,030.85 volts. So you're probably thinking to yourself, this looks a lot like our electric field and Coulomb's law equations. So the only thing that we're changing is we need to make sure that we include our signs. So if we do the same thing for our next one, so we're at a distance of 3 and 4 now, so that's 3 squared plus 4 squared equals 16 plus 9, which equals 5, is our separation distance, and V2 is 1 over 4 pi epsilon naught Q2 over R2. And then this is equal to 8.99 times 10 to the 9. And this is negative 5 times 10 to the negative 6 coulombs over 5 meters separation. So that's 8.99 times 10 to the 9 times negative 5 times negative 10 to the negative 6 divided by 5. And this is equal to negative 8990 volts. And then when we want our total, at that point, we're going to add them together. So V total is equal to V1 plus V2. So that's equal to 6030.85, which is positive, and minus 8990 volts, which is going to equal 6030.85. And then this becomes 1,500. Oh, sorry, I added those, my bad. 6030.85 minus 8990. And this is negative 2,959.15 volts. So that brings us to the end of the notes section of week 4. Join us in our next video where we're going to be going through some Wiley Plus examples relating to these topics that we just covered. I hope you enjoyed, and I will see you in the next one.